So welcome back to the second half of your 7th class in Applied AI, which is our 4th time together, right? Okay, so before the break, I went through the main concept, the rationale, the reasoning, and even a little bit about how algorithmically unsupervised machine learning is done. Basically, the two key methodology we can group our discussion to is cluster analysis, right? And dimensionality reduction, okay? And they are separate, but in a way complementary techniques. But I want to show you basically how things are done. And this is just quickly a recap of what I mean by once and done. Okay, so this is to use the word find cluster. Okay, so if I'll have example for this, by the way, but this is the help page. So basically, find cluster. Just say, you know, I take the whole data set. So imagine this is your raw grade, right? This is your raw grade, and I find the cluster, and the cluster is to separate the low grade students and the middle grade student and very high. So maybe this student stand out really, okay? So you can see that there's a big gap between 25 and the teens, 10, 12, 13, right? And there's a big gap going down to the single digits, okay? So in this case, if this were the raw score, maybe I'll give this student A, the 3 student here, I'll give B, and this 4 student, I'll give C, right? But this is what I call once and done. In other words, it creates a partition and it doesn't memorize anything. Okay, so if I have a new data set, now if it's one dimension, I can stick in and say, okay, there's another student and he get 11 raw score. I can stick 11 right here. Okay, but if it's multi-dimensional, there's no way I can do this. Okay, so this is basically a once and done. It's not meant to be reused. Okay, now if you learn the partition, it's this. Cluster classify. What it means is that it creates a partition and it automatically label one partition or one cluster as 1, the second cluster as 2, third cluster as 3. So these are kind of like automated labeling. And once you have the data, once it's done, okay, for example, in this case, 2 classes, automatically say, okay, there's 2 classes. So now you put in a new number, it would say which cluster it belongs to. Okay, so that's called cluster classify. Now, in terms of method, there's a few things, right? There's like clustering tree, dendrogram. I'm just going to focus on saying 2 groups. One is based on distance, one's based on density, and that's all, right? And the density, this one is also useful, by the way, but the density base, sorry, the distance base, the main one you would use is k-means, okay? So you can read all this individual description of what it does. Again, this is kind of like finding the location of the centroid. There's a density-based cluster analysis. Okay, so an example would be here. This is the example that I was trying to communicate in class, right? So there's a river here. There are 2 villages, the left village and right village, right? Now, if you didn't know any better, I take away the picture of the river. I take away the red versus green. You would have just one data set. The idea is that somehow you have to separate into the left group and the right group. If you use a distance base, you will see that this point and that point are very far apart. So this point is closer to that, right? So in this case, if you were to use k-means, you know, finding the centroid, it's going to lump these guys together and lump these guys together. But this guy is actually opposite side of the river. And, you know, imagine there are alligators in the river, right? And there's no bridge. So it's hard to go from this house to that house, swimming, risking being eaten by alligators or being bitten by hippos. But you can see that there's a contiguous density that can be drawn around this shape. So for the density-based shape, it's better. So I would use density-based clustering technique for this problem. Now, sadly, just as you can't do the eyeball clustering yourself, you can't decide which is best in high dimension. You don't really know if density-based is better or distance-based is better. There may be some indicator and some empirical reason. There's some, first principle reasoning that you can say, oh, this data set should be cluster using distance-based or density-based, but really it is still an experimental science. So like I said, data science is an experimental science. So one of the major one is called DB scan. This is a very popular technique. So if you remember anything, just remember that for distance-based, the most popular is k-means, okay? K being the number of cluster. For density-based, the most popular is called DB scan, density-based spatial clustering of application with noise. Just a brand name, okay? Now, I'll give you an example. Example here is that, I just make a random hue of colors. You can also cluster colors, right? So basically, you can visualize in your head, sort of like red, green, blue chart sort of thing. Well, here's an example of clustering tree. So this is not distance-based and this is not density-based, but this is kind of like clustering tree. So this is even better. Okay, I didn't talk about it before the break, but you can see why it kind of like partitioning. Okay, so as you sort of like go left, right, left, right, left, right, it's separate into the weak yellow, green, purple, bluish, and so forth. And here it's kind of like muddy mixture or something. And this one is called dendrogram. This is also a good way of doing this. Now I'm doing this with color because you can imagine this. Okay, now here's an example of finding cluster. Okay. So if I do define cluster, basically, in this case, define cluster is a once and done thing. It's for this case, I didn't specify how many cluster I want. It happens to give 1 cluster, 2 cluster. So there's a cluster of brownish, there's a cluster of greenish, there's a cluster of dark blue, there's a cluster of purplish, there's cluster of orange and cluster of red. So 1, 2, 3, 4, 5, 6, 7. Okay. Now I could have done this and say, find cluster. And let's do this. Methods. Okay. Is k-means. K-means. And I think I have to put in something like tree or something. Say tree group or something. Okay. Oops. Something like this. Okay, oops. How do I say this? Anyway, there's a way of doing it. It's say I'm going to use k-mean and I want it to be tree cluster. I think let me try again. I think you can shift enter and go to the manual page. I think it's something like this. Tree. Yeah. Does that work? Does that work? There, okay? So in which case, I'm forcing the method to be k-means, and I set k equal to 3. So if I k 3 and 4, 7, okay, so 7 group, okay? So anyway, now that's the once and done, right? Now in this case, what I want to do is I create a classifier. Again, I don't specify. I get the result. The result happened to say, now this is something that I said why Mathematica is a very high level tools, right? If you are in applied digital intelligence, I expect you to go nitty gritty into the technique. But as a BSI student, some of you go into sustainability or health and well-being, and you just want to classify your data, but you're not a data scientist. So what you want to do is sort of like let the Wolfram Mathematica decide for you, okay? So you don't have to say, oh, I'm going to use density-based. I'm going to use distance-based. I'm going to use DB scan. I'm going to use k-mean. I'm going to use dendrogram. You just say, okay, do something that's sensible. Find me some cluster, okay? So that finding cluster, if I don't specify k-means or any method, it's going to select the method for you. So it's kind of automatic, right? So it's a very intelligent way of doing this. Of course, as a professional data scientist, you would do tests, then you will improve and so forth, and you do the tweaking. But if you're from sustainability track or health and well-being, and you just want to classify or cluster your market segment, you do this, okay? Find cluster or cluster. In this case, it's selected for you method called DB scan. So for some reason, this data set, mathematical thinks density-based clustering is better. So there's some kind of internal criteria testing, okay? So it's quite detailed, it's quite involved, and it's select into 6. So now, instead of partitioning the colors, it's just going to label the colors into 1, 2, 3, 4, 5, 6. Okay, so there it is, right? So it's a bit like that, okay? So this would correspond to all the colors that will be classified as 1. And there are 20 in the group 1, 51 in group 2, 10 in group 3, and so forth. Okay, so that's how it's done. Now I'll give you an example. Now that's in colors, but the example we did, I actually will show you this. Okay, this is called if you've been to Yosemite National Park, there's like a attraction called Old Faithful Geyser. Okay, geyser, some people say geyser. I think it should be called geyser. It's basically hot water being spouted from the ground, right? So this is the duration in minutes. So from about 1.5 to 5 minutes of water show. And this is waiting time. So between 50 minutes and 90 minutes. It's how long you have to wait for the spout, right? Right away, can you see what's happening here? Okay, again. Like the example that I showed before class, if I draw this in all black, I'm drawing all this in brown, right? There's no separation, there's no clustering. If I come in and I say, hey, look at it. It looks like it's in a circle. I can describe a circle with mathematics. It looks like ellipsoid. I can draw ellipsoid around it, call it bivariate normal distribution. That's statistic. But it doesn't look like anything, okay? In fact, it's sort of like has a cluster here and a cluster there. And I chose this example deliberately because you can't deny that there are 2 clusters here, right? It's very obvious. Now, you don't have to be a geologist. You can guess what's happening. Underground, there are 2 cavities. One cavity gets filled up with hot steam or water and hot steam. It takes shorter time to fill up, about 50 minutes, 60 minutes each. Once it gets filled up, it shoots, right? Releases, and because it's smaller, it only lasts for like 2 minutes, 2.5 minutes. Then there's a bigger cavity that has longer time because it's bigger, takes about 80, 90 minutes to fill up, let's say, right? And then shoots out with a duration of 4 minutes, 4 and 5 minutes. Okay, and the probability of water filling up the smaller cavity versus larger cavity is roughly the same, maybe a bit more in the larger cavity, right? Let's call it 40, 50, 40, 60% split, right? This is what, by the way, I mean by visualization give you the insight right away. You don't have to be a geologist. You can guess that there are 2 cavities for the hot steam underground water to fill up, right? Now, obviously, it's 2-dimensional. You can eyeball it, right? And in this case, I can also ask you, would you use density-based or distance-based? I would maintain that they give the same answer, right? Because it's such a nice shape, right? It's sort of like a roundish shape, 2 kind of pockets, right? So what's going to happen is I run this. And okay, shift enter. There. So I actually, because I eyeball this, I say I want 2 centroid, and that centroid is the big blue dot you see in the middle. Okay, so the blue dot to the lower left is the average of all the green points. The blue dot on the upper right, or the purple, I don't know what color it is, it's the average of all the upper right purples. See that, right? And there's no, again, because you're actually drawing this yourself, there's no blue amongst the purple amongst the green or greens among the purple, okay? Now, if I did this, okay, and now I want to say, hey, I'm going to give it a label. I'm going to label the green and the purple. And in fact, I can give it interpretation, okay? Interpretation, green is small cavity eruption. Interpretation for the purple is large cavity or cavity B eruption. Now, if a new data point comes in, am I going to do this exercise over? No, right? It's not worth it, right? So I'm going to keep to this learn partition and I'll ask, hey, what's the next data point? And then you say, you know, I have to wait about 90 minutes and it lasts 4 minutes, 30 seconds. Where do you think that came from? Larger cavity, right? Because you would put it amongst the point, okay? Now, if it's something in between, then it's going to give a call, right? So that's what this is all about. This is about learn. If you have a learn partition, I introduce a new point and it'll tell you. So these are all the points, right? So wait 76 minutes, erupt for 4 minutes, wait for 77 minutes, erupt for 4 minutes and ish, okay? So that's what this is. It's called, now if I, okay. By the way, this one, I say cluster classify. I didn't specify that there should be 2, but it's so obvious that Mathematica chose. Now, this is another technique I haven't mentioned by name. It's called Gaussian mixture, okay? Gaussian mixture is very useful in practice, but this is not a data analytics class. But anyway, this could have been k-means. This could have been db scan, and it would probably give you the same kind of answer, okay? And in this case, there happened to be about 97, so about 1 to 2. Yeah, so it's a lot more big cavity, right? Okay, so there it is, okay? Right. So now if you have that, if you have this function, right? Oh, this is an error. Actually, this there. It would classify this as a small cavity, classify this as a large cavity, small cavity, okay? Right. This one I'm going to skip. It's a little bit more example, but I constructed this. The whole point I want to say is that, you know, just because you have nice turtle lumps, like in statistics, if you mix them together, then you can get bananas as well. But nah, I'm going to skip that. Right. So what you want to do, and this is more detail because again, it's for my data analytics class. But the whole idea is that because this clustering is not scale invariant, what you want to do is x1 and x2 to be roughly on the same scale. Okay, otherwise it's going to pay attention to the big numbers. So imagine that x is height and what x1 is height, x2 is weight, right? X1 is height in kilograms, x2 is so x1 is height in centimeters, x2 is height in kilogram. It's going to give one clustering. If you say if it's a height in meters, the number is going to be much smaller. It's going to pay a lot more attention to the weight. Okay, so that's all I want to say. Right. So you prepare the data by selecting the right, thing. Now, this case, I happen to show real data, and this is COVID data. This is something that should be you guys in the health and well-being section should pay attention to. This is basically health statistics, right? And there's a lot of them. I think there's 29 variables. So I'm just going to narrow down to a few. I narrowed down to a few, is it 15 or 12? Okay, these are all the number that I'm going to go really fast here. Okay, so these are things I'm interested in. Case per million, death per million, reproduction rate, vaccination per 100, population density, stringency index, that's kind of like government measure, median age, right? So none of this has that nice normal distribution. Look, this looks like a 3-finger, okay? Population, old population, cardiovascular death rate. It's got nothing to do with COVID, but you know, if you have a high cardiovascular rate, same here with diabetes. If you have high diabetes, then COVID is bad news for you, right? So all this. So you can see that none of them is normal distribution. So you can't do this kind of nice multivariate normality. So what I do is, now I do clustering. So not only do I do clustering, now imagine, now I have, let's say 12 dimension of data. Okay, data are countries or location, like Asia is an average of the whole Asian continent. So let's say there are 200 countries, okay? Each country has 12 health statistics. I want to cluster them together. But if I cluster them together, I can't visualize them. Now, forget about that dimensionality reduction. We haven't gotten there yet. But can you visualize the result? Yes, you can. You can actually do this. The trick is the following. Once you've done the clustering, and let's say you come up with 3 groups of country, you then take the average of the value for each country, basically the centroid, right? Then you use this thing called radial axis plot. Some of you may know from Excel as cobweb. Have you heard of that? Radar plot, something like that. Okay, and it's gonna look like this. Okay, yeah, I might as well show you the big picture. There it is. Okay, so there are actually, first of all, there are actually 3 groups of, or 3 clusters of countries. Okay, and each country, the groups are not evenly divided, right? So what I do is I make the thickness of the line proportional to the size of that cluster. So the biggest cluster is actually the yellow cluster. This is kind of like middle of the road country. There's a smaller group, very small group of country that is kind of blue. And this is a country that I think is quite rich, high human development index, high life expectancy, very low diabetes, right? High GDP per capita. So that's the blue country. Okay. So this is how you before dimensionality reduction, this is how you visualize 12 dimensions together. The thing is, you no longer have individual data point. You can't visualize single country anymore. Okay. So Thailand is in there somewhere. Malaysia is in there somewhere. Singapore is in there somewhere. You just have to find out whether or not Thailand belongs to the green, yellow, or blue group. Okay. But the representation of the green, green, blue, or yellow is the centroid, right? And so you can view, and this is what I mean by interactive visualization. You can view individual, whatever, but it's not that interesting, okay? And you can do some kind of scaling. Fine. So you do this, and you can encapsulate it as a tool. Now, I did tell you that everything, in a way, even though you have the principle, it's experimental. So if you did this with one technique, you get one clustering. If you did it with another technique, you get another clustering. Sometimes it depends. What happened with my client is my clients would come up to me and would ask me to do sort of like a consumer or customer segmentation. So basically this kind of exercise, right? And it's not clear whether or not I should use K-means. Usually K-means work, but let's say, I don't know if it's K-means or DB scan. If it's K-means, it should be 5 group, 3 group. So sometimes I present alternative, right? So I present not just one of these radar plot, but I present 2 or 3, because after all, it's about utility, right? So this, if this were not groups of country, but segmentation of customer, then you can say, oh, hey, I divide my sales force into 3 teams. Okay, something like that. This is another technique. It would result in something like this. Now, would this be good if this were a market segmentation? Well, it depends. It depends. The first one looks better because I can segment into 3 similar size group, right? But different focus. Maybe high net worth and low net worth. And so it's about, a third of a client base. This, on the other hand, means what? Hey, maybe I have a huge client base of yellow. Then I have a very high net worth, selective 1% of blue, right? So for some market segmentation, maybe this kind of clustering works better. I don't know, okay? But this is not market segmentation. This is COVID data. Right. So that's that. Okay. And that's another technique. So I would present many things. Now, this is dimensionality reduction. And long story short, this is what you do. So in my, this is a whole lecture in my data analytics, so I'm not going to give it to you here. But the point is that you can do dimensionality reduction and compress original dimension of 20 down to 2 to visualize, okay? What happened is, the way I recommend, and I actually show the way I don't recommend in the book, and the way I recommend is use the original dimension, appropriately scale so all the variables have roughly the same numerical size. Do the clustering in the original dimension. Visualize using radial axis plot. But if you want to visualize individual data plot, you can do that by downward projection from original, say 12 dimension down to 2. Okay. Now, that's it. That's the end of the lecture on unsupervised learning. Now, the last thing, and this is very important. Yeah, I think that's good. So imagine, right? Again, I'm going to use that example of houses on the street. Okay? Houses on the street. So again, I said, yeah, there's no one-dimensional, one cluster analysis. So this would be maybe a 2 cluster, but if you think about one cluster, it's like saying, hey, are you not using the full space? That's my that's the sort of question, right? So geographically, you have 2 dimensions, but because everybody wants to build a house on the road, nobody wants to build a house in the middle of nowhere, you're not using all the space, right? So in this case, the shape that I'm describing, well, yeah, it does matter that I say, okay, it looks like this N shape, but more importantly, the idea is that if I have a spline, in other words, instead of using this as X1, X2, okay, I do this. Watch my hand. I'm going to use red. What if I do this? And I call this direction A1. In fact, because it lives in one dimension, I only need one artificial dimension, right? Right? So now each house address is a point on one dimension. That's pretty cool, right? That's pretty cool, okay? What it means is the following. First of all, imagine, okay? And well, this is not unreasonable. This is a city center. This is a city center. Okay? The city center, okay? Imagine, right? I'm predicting house price. What would happen if I put in X1 and X2? It's going to be a terrible model, right? Because you say house price is F of X1, X2. Okay. Now, this one happened to look like a snake, but if it looks like a line, in statistic, you can write this down and ask your friend. The problem is called multicollinearity issue. It's saying that your x's, even though you have 2x, they don't spread out in 2 dimensions. They get stuck on a line. So it would be like saying, I'm going to fit a surface on 2 dimensions, right? So I'm going to fit a surface on 2 dimensions. That would be like putting a tabletop on the legs. But instead of leg being spread out in 2 dimensions, all the legs is lined up. Is that table going to be stable? Right? Imagine, right? You have table, right? Table is stable because it sits on 2-dimension basis. That dimension is top left, top right, bottom left, bottom right. So it fits very stable. Imagine if instead of the 4 legs being on separate like this, the 4 leg lines up in a line. Would you make a good table? It was going to wobble, right? Likewise, data fit is going to wobble, except it's not a line, it's a snake. So this is a bad model. Whereas H is equal to F of A1 is a better model. Okay. So actually, small number of variable is better. This is something I want to tell you, okay? The dimension of the data should correspond to the degree of freedom of how the data is spread. If the dimension is bigger than the way the data is spread, then you have a problem. Then the model is basically, it's going to try to fit something that doesn't exist. It's like this model is trying to fit here, here, but that is never relevant, right? That model of X1, X2 is not going to give you the right expression for the house price. However, if you just measure it as a function of distance A from city center, you can say the further out it is, the cheaper. Let's say, people like to be in the city center. So if I ignore everything else and I say, A, this is going to give you a better model. It's going to be more accurate model. The one that's closest to city center is very expensive. Further out, cheaper, right? So dimensionality reduction is not just for visualization. So number one, write that down. Dimensionality reduction is not just for visualization. Somewhere out there, there's an optimal dimension that you should downward project to. Okay, somewhere that contains all the degree of freedom. Problem is, just like anything else in data science, you don't really know what it is. Okay, so whereas if you have a population with 8 dimensions, and the dictator say, I want 2 dimensions because I want to see it. And you go down to 8 to 2, right? But if you want to make some kind of model, and that 8-dimensional population actually lives in a 5-dimensional data manifold or subspace, who's going to, it's very hard to determine. So I'm not telling you it's easy, okay? But there's a concept there. There's a concept there that even though nominally we have 8 dimensions, the data only lives in 5 dimensions. Even though houses live in 2 dimensions, in reality, there's only 1 degree of freedom along the road. So there's only 1 actual dimension. Okay. Now, that actual dimension is going to be some kind of combination, some kind of function. In fact, it's a snake function of X1 and X2, let's say, right? Fine. But would you agree that this is better? This is bad. This is good, right? It's bad. So number one, dimensionality reduction is not just for visualization, although it can be used for visualization. Number one. Number two, and this is very important, AI can only read numbers. Okay, write that down in your head. AI can only take in numbers. I'm going to call it a vector. You say, wait a minute, didn't I just talk to ChatGPT? Didn't I just do that? Didn't I just do this? The reason ChatGPT can do that and do this is because there is an interpreter that takes whatever you say to it, which is text, into vectors or a stack of vectors. Anyway, it's kind of numerical array. I'm just going to call it vector for now. It's actually maybe a tensor or whatever. So basically, AI can only read this number. And in fact, it also only produces this as well, okay? Okay. Why? Because AI is a program. AI is a computer. You can't give computer food. You can't give computer banana. You can't give computer a song. You can only give it numbers, right? In fact, for nominal data like male and female, do you put in male and female? Actually, no, you have to interpret it. Male is equal to 1, female is equal to 0, and then machine understand 1 and 0. So point number 2. Okay, point number 2. Now, let's say the optimal dimension is n. Okay, optimal dimension is n. Okay, just like before, right? The street, 2 dimension, the optimal dimension is 1. Population of 8 dimension, the real manifold is in 5 dimension. So 5 is the optimal, let's say, okay? So I say A is the optimal dimension. So even though you start with M, which is bigger than N, okay? So you start with numerical, which is M, you should downward project it to N. Okay? So the word is projection. When you put one thing in one space to another thing in another space, okay? In popular parlance, it's called avatar, right? In mathematics, it's called projection. Okay? If you can go from human form to avatar and back, then it is isomorphic. You can go back and forth, right? If you go to become an avatar, but when you come back to human, it can be anybody else, then it's not isomorphic projection, okay? So projection is a location of entity from one space to another, and hopefully back, okay? Well, here's the deal. If the information is not lost, in other words, because houses live on one street, when you reduce from 2 dimension to 1 dimension, do you lose address? No. So it is isomorphic. You can go from 2 to 1, 1 to 2 anytime. If the houses don't live on the street, then yeah, you have a problem. Okay? Because then you have 2 address, 3 address. Let's say imagine that the street has 2 sides, left side and right side, and they both share the same distance, right? So if you have a street that looks like this, right? And you have one house here and you have another house here, and you say, oh, it's 1 dimension. Well, these 2 houses are the same then, right? So that doesn't work. It's not 1-to-1. In fact, if there's another one here, it's not 1-to-1, okay? 1-to-1 means you can take one guy to one guy, and that one guy comes back to the same guy. So kind of like 2-way avatar, okay? Reversible avatar. So that's called isomorphism. The point is, the reason N is better is because N is smaller than M, and yet it preserves all the information, all the degree of freedom, all the differentiation, all the identity. Okay, fine. Imagine, okay, somebody else look at this and say, AI reads array of numbers, say vectors, n dimension. There's an interpreter that reduced the m dimension down to n dimension. What if, just for fun, there is some kind of ghostly space, very abstract space. Okay, what I mean by space is, you know, where you have different possibility, abstract space of something. And I can do this thing as well. I can take it and map it to here and back. Okay. Now this thing, I don't know if it's bigger dimension, it's not numerical, it can be anything abstract. So I'm not going to call it projection. I'm not going to call it isomorphism or mathematical name. I'm going to give it a name called embedding. What I mean is I embed a point to one vector, a different point to a different vector. Can I do that? Conceptually, you don't know how to do it yet. An abstract possibility of something, a dream space, where every instant of dream is mapped into a row of number. Another instance stream is mapped to another row. You can do that, right? Well, conceptually. This is called embedding. Now let's make it concrete. That space we're talking about is a space of language. In particular, I'm just going to say space of vocabulary. Okay, vocabulary. Okay, now let's say, English word has 50,000 vocabulary. It's like 50,000 house. What is the easiest way of doing this embedding? List them in a dictionary, right? So this dictionary has 50,000 words. The first word, artwork, this is an animal, okay? It's mapped to number 1. And zebra maps to number 50,000. You can do that, right? You can do that. So, and technically, that's an isomorphism. You can go back, right? From zebra to 50,000, 50,000 back to zebra. Nobody complains, right? No problem. Okay. The problem is, and it's a problem, that notion of closeness is gone. Because in word, there is such a thing as a closeness. I can, tell me if you disagree. Cat and dogs are different, right? But the difference between cats and dog is probably smaller than the difference between cat and refrigerator. Would you agree? Right? How would you do that? Well, because it's animalness. Okay? Animals. Well, this is kind of like Western centric, right? You kind of look at things by what it is. Well, you know, in Africa, let's say one plant and another plant are different, but the difference between plant A and plant B is smaller than the difference between plant and spring. Yeah, because spring is a season, right? Plant A and plant B are close together, but they're different from spring, summer, fall. But to these African tribes, and this is actually linguistically relevant, their idea, this plant is closer to spring because you plant that thing in spring. It's closer to spring than it is closer to this plant because this plant is only relevant in summer, something like that. So wait a minute, how do we talk about closeness? It's very context dependent, isn't it? Right? So in order to maintain closeness, how do you find closeness? If it's one dimension, the closeness is just a subtraction, right? If it's 2 dimension, it's also subtraction, but in 2 dimension. Let's imagine that you have something that should be close together, close together, close together, close together. Okay, watch this. This is an optimal dimension. Why? Because this is so close in both horizontal and vertical. This is close in horizontal. Close in horizontal. These two are far apart horizontal, but close vertically. These are close horizontally, but far apart vertically. You get the point, right? So there is an optimal dimension to represent the distribution of context. Okay, so imagine these are words, and this word happened to be cat, dog, refrigerator. Say cat, dog, refrigerator, oven, and tractor. And so this is kind of outhouse. This is in-house. This is tiger and lion. Okay, so maybe this is kind of domestic animal. This domestic appliance, farm appliance, outdoor appliance, heavy duty appliance, and then outdoor animals. Okay, so you can imagine that for that representation of context closeness, 2 is good. 2 is good. Well, when we started this research in the, not we, I don't mean I mean, you know, the computer scientists, in 2010s, 2013, 2015, and so forth, right? We were talking about embedding English language in a space of 300 dimensions. 300 dimensions. Now, technically, that's the number I use, but it's not the real number. GPT, now that's what we're getting to, uses the dimension they use is, I think, 12,880 dimension. In other words, they map all the 50,000 English words into each of them into numbers. And how many numbers? 12,880 numbers. That allows different words to have closeness like this. Okay, I think it's 12880. Okay. That n equal to 300 or 12880 is therefore called embedding dimension. It's called embedding dimension. Okay. So before you get to GPT, GPT works with language input. Okay. The only way you can input language is to turn words into numbers. This is called word to vector mapping. Okay. So the most important thing that has to happen first technologically is, when I was your age, statistic people, they use y is f of x is numerical. When I was your age, I was working with numerical data, neural network, multi-layer perceptron. So sort of like modern day, old day equivalent of today, so all this artificial neural network. But basically, I was working with numerical input. Now, if you want to work with text input, you have to turn text into numbers. So word to vec is the way it does that. But it has to do it in this way that preserve closeness. And this is where you get to this thing where the 300 or 12,880 that mentioned. So a representation of the word boy in the embedding space. Here, the word embedding dimension of girl is here. Boy, girl, okay? And then you have another thing called uncle. It turns out that in this space, you can do algebra, you could do addition, vector addition. You can say uncle plus girl minus boy. So this thing, this stick here, this arrow here is girl minus boy. Take this girl minus boy, attach it to the head of uncle. So it becomes uncle plus girl minus boy. What do you think you find here? Around here, you have a space in the embedding space. And if you look around, the closest one you will find will be the word aunt. Won't be exactly, it'll be close. That's why you can do this word algebra. Okay, uncle minus boy plus girl equals aunt. So that's what I mean by closeness. Girl and boys are close. Uncle and aunt are close. Okay, but in this dimension, boy is close to uncle, girl is close to aunt. So this closeness, this algebra, this is called embedding bracket vector space, embedding space. So that's the first thing that has to happen. Okay. So that basically say, I stick word into AI. Now, I told you, right? AI separate largely into two groups. One is generative, one is predictive. And what's the job of predictive? Is to get the answer that makes sense, okay? It makes sense in terms of predicting the right Y. It makes sense in terms of clustering the data correctly so that one group is separate from another group. So it has this ground truth to it. But what if what you want is the output which is not grounded in reality, however, is grounded in context relevance. In other words, I'm asking you, what year is it? And you said, this year is 1960. It's not correct. But is it context relevant? Yes, I'm talking about years. Okay? So if I ask you what year is it, and you say 1960, you're wrong, but you're context relevant. I ask you what year is it, you said Apple. That's not relevant, right? This year has a lot of hurricane. I ask you what year is it, and you give hurricane. Well, not really. Not really, right? It's kind of like a lot of leap before you get to this year to hurricane. So the idea is you want to be context relevant. Okay. So the example I used yesterday, I'm going to stick with that, even though it's not a very nice example, is the word snake. Snake is close to many things, right? So original embedding is snake. Okay, snake has a representation here. However, if I want to talk to a ChatGPT about snake, it can mean many things. I have a pet snake. I have a pet snake. My friend backstabs me, say bad thing about me. He's a snake. Same exact word, but based on what came before it, this snake actually is a different thing. So you have to think of, hey, I have to be able to sort of like take the original embedding or location in the vector space or embedding space of snake and kind of like traverse around it, travel, but not in the algebra way, in a more like a context way. Sort of like snake. What do you mean snake? Literal snake? Pet snake? Or hyperbole snake? My friend is bad. He say bad thing about me. He's a snake. That is a way, the way you can do that is to look at the word that came before it. Now, when you talk to ChatGPT, I may have said this, it looks like you're having a nice conversation with it, but you know, all that ChatGPT does is predicting the next word that makes sense. Okay. So if you're talking about predicting, and the way you predict is to look at the back. Remember the beginning of the class? What kind of problem that is? Autoregressive, right? Except this kind of autoregressive is not looking at today's rain, yesterday's rain, the day before's rain, predict tomorrow's rain. That's predictive AI because I have ground truth to predict. This is about looking the present word, snake, the previous word, pet, previous word, I have. So the next word is, let's say something like, they say, pet snake. What kind of animal is it? Okay, the prediction would be, well, it is literally a reptile, not a human being. Okay, whereas you have a snake, and the previous word is, he is like a snake, he is a bad friend, or something like that. Then the prediction would be human being. Okay, so you can imagine that you have this kind of predictive ability that is looking back, as if you're doing autoregressive. But you're not rewarded for correctness, you're rewarded for relevance. Okay, relevance. So, you know, whatever you make conclusion about the snake is do you make, okay, let's say snake, I have a pet snake, okay? And the question would be something like, can my children play with Bob, the pet snake? Okay, maybe the wise answer would be no, because children don't know how to play with snake, let's say, okay? But it could give you the relevant answer, which is, yeah, go ahead, play with Bob, because Bob is a pet. Now, the answer would not make sense if you say play with Bob, who's a friend, right? My kid shouldn't play with my friend, let's say, but my kid should play with a pet. The answer is wrong because the pet happened to be a snake, right? So it's a wrong answer. However, if you add certain things like, I have a pet snake named Bob. My other friends also have pet snake, but that pet snake bit his children. Now there's context, right? There's kind of like reference to it about, hey, snake bite. So I'll say, would my children be safe? Would snake bite my children? Yeah, maybe. So the idea of having this information input as context, that's what we call context length. And with ChatGPT, this context is, how long is the context window? I don't know, depending on version, but let's say you have about 2-3 pages worth of context window. In other words, all the things you want to prime the information so that you can condition. So you modify the meaning of snake, reptile, or snake, human. Okay, this is kind of like movement in that kind of like abstract space. Depends on what came before it. And what came before it with ChatGPT is about 2-3 pages, let's say. Okay. By the way, I keep saying that the word is embedded into a vector space. In reality, it's actually not the full word. It's what's called token. So like the word information, this could have been broken into inform and formation or something like that, or inform and Asian. Okay. So Asian means some noun version of something. And inform, yeah, that's a word. So maybe this information is not embedded as one word, as one address, but 2 address. Okay, so 2 tokens. So again, English language maybe has 50,000 tokens corresponding to 40,000 actual words or something like that. And also other things that are not word like bracket, comma. That's why when you chat with ChatGPT, comma and all this is taken into account. Okay. Right. So what happened then is this AI, okay, takes this. This can be bigger dimension. This could be word. Well, people are going to say, hey, maybe there's other things that's defined in context. For example, chemistry, right? Is there a notion of closeness? Yes. If you're talking about, let's say, elemental chemistry, right? If you go down periodic table, if they're on the vertical, they have similar chemical, right? So inert gas will be close to inert gas, right? Metallic element will be close to metallic element, right? So you have this kind of closeness in chemical element space. So maybe I put in periodic table. Well, if you put in periodic table, why not put in library of molecule, right? Molecular space, right? Why not protein, which is a specialized but very complex molecule, right? Okay. If you can do this, maybe you can do something like, hey, life is based on carbon. What else could life be based on? And in that space, carbon happened to sit on top of silicon. So maybe you chat with ChatGPT and say, hey, if life could be based on carbon, what else could life be based on? It would probably say silicon, because silicon is close to carbon in that space, right? Likewise, so this is all kind of stuff. What else? This is what I'm really interested in. Graph. Graph is like relationship between, network. Network pattern can be embedded. For example, very easy, straightforward, right? Let's say right now, the network of people in this class is people that you can touch in arm's length. You connected with 2 people, connected 3 people, you connected with 1, right? That's the network. That's my network, right? Well, in this network space, these nodes are probably close together. Now, these 2, even though not connected, are probably closer together than these 2, right? And that happens naturally. So you can think of embedding graph. Okay. So two things happen in, the first thing I want to say is that all this embedding technology gets you into AI. If that AI is trained to approximate real truth, then you're talking about predictive AI. So people who would say something like, if I put in this protein sequence, what is the likely behavior? This is what we did with some COVID vaccine, right? Basically, at the micromolecular level, protein spikes, these are geometry, basically, a very tiny geometry created by the shape of the protein. So protein is a sequence of amino acid. Each of them has attraction basis. Think of it as a string of magnets, okay? So some magnets like each other, some magnets don't like each other, and there's a big magnet, there's a small magnet, there's a this shaped magnet. So you have a string of various magnets, okay? So some positive pointing up, negative, and then you sort of like, boing, let it lump together, right? And based on that attraction, it's gonna form a shape. And if it form a shape that looks like thing that should enter your cell, that's how the virus get inside your cell, okay? Because it happened to shrink into the shape of a key, okay? Your cell has like an opening. It looks like, let's say, this shape. And the virus happened to have a protein sequence that has this shape. So connects, right? So what is mRNA vaccine? Well, you don't want the you don't want the virus, but you want the cell to know this guy, right? So they create mRNA using your own cellular machinery to produce this shape, produce the key and flood the system. The system say, this is a key, it's alien, let's kill it. So next time the virus comes with that key, gets killed, okay? Right, so this is what gets you AI. The difference between predictive and generative AI is basically here, you want something that is, in a way, ground truth, right? Versus you want something that is relevant to context. Okay. Now, technical term, how do you make it relevant to context? You have to memorize what word came before it, okay? In 2016, I went to California to a conference, and I could swear in 2016 conference in California, every third paper is about this thing called long short-term memory. It's saying that to understand the context, it has some kind of state register that kind of like memorize what came before, okay? So whatever came before, adjust this parameter, and this parameter influence the output. That's called long short-term memory, okay? That was the thing, okay? Just about, every 1/3 of all the papers, and the whole conference is flooded with people talking about STM, 2016. Well, 2017, something else happened. Instead of maintaining some kind of parallel track of memory of what came before, they have this mechanism where it's literally say, this word, which is snake, should pay attention to the previous word. But which one? That can be tuned. So it could be paying attention to the previous word, which is the word pet, previous word, which is backstabbing friend. Based on that, it knows what context it is. So in other words, it's looking at back 2, 3 pages of text, but it doesn't look at all of it equal weight. It's paying different attention. So one way is to pay attention to the modifier, like pet snake. One way is to pay attention to naming, like Bob, okay? So each way of paying attention is called attention mechanism. And there are many ways, so it's called multi-headed attention. Anyway, the point is that the paying attention takes the original embedding of snake, which is a vector, just a series 12,888 number, and keep transforming based on the attention to the previous words. keep transforming, keep transforming, keep transforming, so that it aligns better and better and better with context. Therefore, this technique is called transformer. So when this transformer, look at the historical context, it's not charged with the task of predicting some truth, some ground truth, but it's tasked with saying something that is plausibly connected or context relevant. The job of this transformer is generative. And because this architecture contains, wait for it, 175 billion parameters, this thing cannot be retrained. So OpenAI or Google, I keep getting it, OpenAI, right? So OpenAI spent billions, well, I don't know how many. They have like array of GPU, very expensive GPU card from NVIDIA 800. They have like 10,000 of them, I think it was. And they ran this thing for like 8 months to train the 175 billion parameter. Once it's trained, it's fixed. You keep that parameter. Remember back when I talk about machine learning as parameterization? Well, those network parameters is called weight, and it's pre-trained, so it's fixed. The parameter is fixed. Okay, so that's it. No more change. The 175 billion weight parameters are fixed as of, I think, December 2023. That hasn't changed. That's why I say when you give it information, you just add in context. You're not retraining the model. Sometimes they call it one-shot training because you give it additional example. Yeah, that's just giving it context. You're not rerunning the training algorithm. Okay, nobody can. So it is a transformer architecture performing generative tasks. It's so big, it can only be pre-trained. It only makes sense to call it generative pre-trained transformer, GPT. That was it. And the GPT can then do all kinds of stuff, but the stuff that is used, that you're familiar with, is conversation, so ChatGPT. Now, before I finish, I'm going to tell you this is your world. Your world, well, first of all, your world can do what my world did, which is something like numerical prediction. Here and then predict some value. Okay? Prediction. However, this is where your world differs from mine. It's no longer just numbers. You can put in all kinds of stuff. Text, video, whatever, picture, all kinds of stuff. Moreover, the output is no longer, something that is that has some kind of ground truth, but it's some kind of generative power. Okay, so this is kind of like creative reward. Okay, so it's like when you teach a baby, your kid, this is apple, this is banana. You're not asking your kid to be creative, right? All right. So imagine that after your kids have learned how to make banana and apples, you say, okay, little Johnny, what would banapple look like? That's why he gets a little bit creative, right? Banapple doesn't exist. There's no banana and apple hybrid. So the kids draw, Mommy, this is what banapple looks like. Oh, good, creative. It's relevant because the picture that the little Johnny drawn doesn't have chainsaw in it, doesn't have refrigerator. It's not mechanical. It's fruit, but it's a weird fruit. So it's not correct because nobody has ever seen what a real truth banapple looks like. But the child knows that your mom wants, the mother wants him to draw a fruit. Context relevance. Okay. So all this generative stuff, this AI, Sora, video. Now, all this, so there's two things that has to happen, two technology. One is called embedding. Okay. And there are different techniques. And the other one is called transformer. The reason it's called transformer and the technology that's game-changing transformer is because techniques like in 2016, long short-term memory architecture didn't work so well. It works well in a very small set of numbers, problem. But transformer works with text. Transformer also works with picture. If you think about it, I show a picture of a cat, I show a picture of Alice, and I say, draw me a picture of Alice holding a cat. It has to look to that cat, not any cat, not generic cat, right? It has to be that Alice, not Alice in Wonderland, right? So it has to pay attention. So this context relevant. Now, it doesn't matter how it holds the cat. That's the creative part, right? Doesn't matter how banana and apple is combined. Doesn't matter if the Alice hold the cat over here, as long as it has that context relevance. Yeah, it's that Alice I showed you earlier. Yeah, it's that cat, right? So you can do video generation. Now, last thing is this embedding space is mathematical. It's universal. So when I said snake have to pay attention to the word pet, right? Actually, it's not word paying attention to word. It's actually vector paying attention to vector. Now imagine if it's not word vector, pay attention to word vector, but picture vector, pay attention to word vector. Or the other way around, word vector, pay attention to picture vector. That's when you do things like give the picture, output, and notation. What's happening in that picture? Picture to text. Or you can say, draw me something. Word is a context, right? But the thing that you want is the generation. So it becomes multimodal, interoperable. Text, video, all these things can cross path, right? So you go from text to word, word to text. This is another magic. So this embedding, if you ask me, by the way, if you ask me, this is the real thing that you have to thank. Okay, this embedding is so powerful. It's basically, if you have to think, anything can go into mathematical engine. Not only that, it doesn't have to be the same thing. It can be word with text, text with word, word with sounds, all kind of stuff. But once it's there, then this transformer is a particular technique. Happen to be the most successful right now. Okay, so I can imagine in 5 years' time, a new architecture comes in and beats transformer. But no matter what, I think the embedding will stay. It just be different technique, but you see what I mean? It's a different kind of thing. One is a particular technique. The other one is kind of like the whole workflow. Okay, turning things into numbers. That is amazingly powerful. That's amazingly powerful. Okay, so that's your world. Now, again, this class is supposed to be hands-on AI, so you're gonna play with things. But if I have time, maybe I'll come back and give you maybe half a lecture, maybe on how GPT or transformer works under the hood. How does it pay attention? That sort of thing, right? But the most important thing is to work with this. Now, I'm gonna preempt, give you a preview after the exam, midterm exam. My part, my every other week will be handed over to Gongkan, right? Gongkan is gonna teach you about what's called agentic workflow. That'd be like this. If you ask ChatGPT, it's going to give you sensible answer. It doesn't have to be correct, right? If you ask Google search, let's say only search Wikipedia, it's going to be correct because it's based on, let's say, established fact, but it doesn't have to be relevant, right? So can you imagine if you ask ChatGPT to know based on the context, what you want? Okay, so for example, snake, pet. What else, what other reptile makes a good pet? But now I don't want it to learn from pre-trained. I don't want it to take my context about, I have a story that pet told is bad. I want it to actually go in the internet, open Wikipedia API, look up the word list of pets. Okay, in which case, I'm not using generative AI as an intelligence engine. I'm using generative AI as an sort of like operating system, like my assistant. Go fetch this information, prepare it for me. It's kind of operating system. Okay. To do that, then you power the the GPT power to understand what you want, context again, relevant, with genuine fact, like, you know, what list of pets in North America or something. Okay, from Wikipedia page. And to do that, you need a framework called agent. Basically, you just kind of like create an agent which is driven by GPT, but that agent does things for you. Doesn't just give you answer from what it knows or what it thinks, but actually go to do things. Go look up Wikipedia, go run statistics analysis, go run Wolfram Alpha Mathematica program, come back and so forth. Simulate this, simulate that. Okay, there are actually agentic AI that does very amazing thing, like enters a hackathon. Okay, enters a security, what I don't know what it's called, securiton. It's a hackathon for people who try to break security. Okay, so it's like a security breach competition. Okay, and so there's like a language model that try to breach a security protocol or something like that. So it's kind of a very agentic agent. Okay, with that, I'm done. Again, I may come back and give you a peek under the hood of how transformer and stuff work and so forth. But for now, I think you are on your way to play with this. Okay, and again, you're playing with two things: playing with trying to find ground truth, or playing with generative capability.
Anything you guys want to ask about stuff, including, of course, next week midterm exam that is on Tuesday, so not Wednesday morning, it's going to be on Tuesday morning. And you can bring one sheet of paper, handwritten or printed, 5 questions about. Anything else? Yeah. Huh? Yes, both sides you can use. No, no, it is really written answers. Yep. Come again.
Nobody knows.
It is going to be like explanatory or like calculation.
Mostly it's about storytelling. So things that we have learned over here. The content is really the videos and then the slides from my lectures. And there's hardly, honestly, you don't need to write Python code, really. It's about explaining some content and applying the knowledge that you got from here. Yeah. All right, see you next week.